Chapter 4, Lesson 32 is going to be, again, on zeros, but now we're not going to just find real zeros that we had before. We're going to do imaginary and complex zeros as well. So when you start dealing with imaginary and complex zeros, the thing to know about those is they always come in pairs, assuming that you have real number coefficients. We're not going to talk about a polynomial that has imaginary coefficients like x squared plus 3ix, where there's an imaginary number somewhere in that polynomial. We're just going to deal with real number ones. So in any case, when you do have that irregular old polynomial like we've been talking about, they will always come in pairs. So if you have, say, 8i, you're going to have a second imaginary number in that as one of the answers as well. So what this is called is complex conjugates. It's a term that you're going to hear a couple of times, so you should probably know what that is, because I may just ask for it. So if you have 4i, the complex conjugate of that is negative 4i. And if you had 5 minus 4i, the complex conjugate of that would be 5 plus 4i. So it is the imaginary number part that changes the sign. The real number part stays the same. So when you have your complex number here, real part, imaginary part, notice it's the imaginary part that changes the sign and the real number stays the same. All right, so if I had a polynomial of degree 5 whose coefficients are real numbers and has those 3 zeros, I want to find the remaining 2 zeros. So regular old real numbers don't necessarily come in pairs. So that was when we were talking about multiplicity. They can, but if I have negative 2 as an answer, that does not mean that I have positive 2 as an answer. I could, but I don't know that I do. But with the imaginary / complex numbers, I do know that those come in pairs. So I would get another answer from the negative 3i, and I would get another answer from the 2 plus 4i. So if I started off with 3, I get another one to match with this and another one to match with this. There's my 5 answers. So again, we use the complex conjugate for it. So negative 2, just an answer. Negative 3i will give me positive 3i. 2 plus 4i would give me 2 minus 4i. So these two would be the remaining zeros. And in a problem like this, this will be a read the directions type of thing. So this one literally just wants you to find the remaining zeros. There'll be other ones that'll ask you to find polynomials and things like that. This one literally just asks for the other 2 zeros. Make sure you're answering the correct question. All right, so when you're given zeros and asked to write a possible polynomial, like I was just talking about a second ago, this is how you would do it. So before, if I had, you had done these examples, or an example like this in a previous problem, or previous section, excuse me. So if I had zeros of 3, 1, and negative 2, and negative 2 had a multiplicity of 2, degree of 4, so 1 answer, 2 answers, 3, 4 answers, because of the multiplicity of 2, you do x minus each one of those. So x minus 3, x minus 1, x minus negative 2, so x plus 2, and because this has a multiplicity of 2, you would write that as squared, and there's your polynomial. So again, no, because you had 3, you don't put down negative 3 as an answer. It turns out that it's not on this one. So it's only the imaginary and complex numbers that you're switching on. The imaginary part, again. Okay, so what if those zeros were imaginary and complex? So, degree of 4, these two is zeros, so I'm also going to have negative 3i and 4 plus 2i for my total of 4 answers. All right, so to figure out what the polynomial would be, I'm going to take, let's do this part first. Okay, I'm going to do a little arithmetic here to figure out how this will look as a polynomial. So because they come in pairs again, I would have negative 3i as one of the solutions as well. So what I'm going to do is I am going to say, because I have 3i and negative 3i, I'm going to write that as positive negative 3i and set that equal to x. Then I'm going to square both sides. And when I square the positive negative, it just becomes plus. Again, because if you square a negative, it's a positive number. Negative 3 squared is 9. Negative 5 squared is 25. It's not negative 25, it's positive 25. So when I square the plus minus, it's going to be a positive answer. So 3 squared is 9. I squared is I squared. I squared, remember, is equal to negative 1. And because of that, then I would replace that with negative 1. Negative 1 times 9 is negative 9. So x squared is equal to that. Move the 9 over to the other side, and I now have my factor of x squared plus 9. Then I'm going to do the same thing with 4 minus 2i. So I would have 4 plus 2i as well. So that means I'm going to have 4 both plus and minus 2i. So I'm going to do the same kind of idea that I did here. I'm going to write x is equal to 4 plus or minus 2i. Now, on this one, I just then squared both sides. I'm going to move this 4 over first. I want the imaginary number part to be by itself. So I subtracted 4 to the other side. Then I'm going to square both sides. Okay, and again, this right-hand side will then become 4i squared. This would be x minus 4 times x minus 4, so you have to FOIL that. So x minus 4 times x minus 4 would be x squared minus 8x plus 16. 4i squared is negative 1, so that'll become negative 4. Add the 4 to the other side, and you have your factor. All right, so let's actually write a polynomial with this now. So I want real coefficients when I do this. So you cannot leave answers of x minus 4i and x plus 4i. You can't have any imaginary numbers in your polynomial. So anytime those pop up, that's the only thing that you're going to have to multiply together. Okay, so degree 4, here's 3 of them. We have an imaginary one, so again, that comes in pairs. So negative 4i would be my fourth one. So I'm going to do the same process that I did on the previous problem. I would do x is equal to both positive and negative 4i, square both sides, make that negative 1, move the 16 to the other side. And then I would do x minus the other answers. So I would have x minus negative 2, so x plus 2, x minus 1, and my x squared plus 16, and that would be my polynomial. You could multiply it out further if you wanted to, but this meets the requirements so that I have real numbers in my answer. Okay, so I prefer you don't multiply it out because it's just going to waste time and you could possibly do that wrong, but I guess technically you could if you wanted to. This would just be what we would consider factored form. All right, let's do another one. Fifth degree polynomial in factored form. So that has 1 with an even multiplicity, negative 2 with an odd multiplicity, and 3i. And then we're going to throw another thing in here. I want a y-intercept at negative 36. So this, if you can understand this problem here, then you understand a lot of stuff that we've done before this as well. All right, so I'm going to start off with the fact that if I have negative 3i, let's do this a little bit here. If I have positive 3i, then I will also have negative 3i. So when I work my way through that one, I'm going to have x squared plus 9. Then I'm going to have x minus 1 and x minus negative 2, so x plus 2. And because, didn't mean to do that, sorry. Because this has an even multiplicity, I have to have an even exponent on that. And because the 2 has an odd multiplicity, I have to have an odd exponent on that. And it does have to total up to 5. So I have my x squared plus 9 from over here. Then my x minus 1 with an even multiplicity, so I chose to put 2. You could possibly put 4, 6, or 8, but I do need it to fit into a fifth degree, so if I put something bigger than 2, it wouldn't work. And then x plus 2 would be to the first power. So I have x squared here, x to the first here, so that'd be my total of 5. So that meets my fifth degree. And then we're going to go back to, if I have a y-intercept, how do I find the leading coefficient here? So that was, if you remember from a couple sections ago, plugging in 0 for x and negative 36 for y, and then solving for a. So when I do that, I will get negative 2. So therefore, f of x would equal negative 2 times the x squared plus 9 times the x minus 1 squared times x plus 2. So that would be 5th degree y-intercept at negative 36 with these pieces. So if you can do that problem, then you can pretty much do any problem that I'm going to throw at you in this section. Okay, so let's do one with all imaginary and complex zeros. So degree of 4, 3 minus I, 3 minus 5i. All right, so let's do this again here. So let's start with the 3 plus 5i on this one. So again, you need to do x is equal to. That's the big mistake that people make on this one. They just try to put 3 plus 5i and 3 minus 5i in a set of parentheses. You need an x along with it. Everything should have an x that goes along with it. So x is equal to, move the 3 over, square both sides, and simplify. So when you do that, you'll get x squared minus 6x plus 34. And then with the 3i, you would have 3i and negative 3i. X is equal to, square both sides, move the 9 over, and you've got that factor. So x squared plus 9, x squared minus 6x plus 34. Again, you do not need to multiply these together. You have all real numbers here. So at that point, you are good to go. Okay, so for this one, now I'm going to take the idea that I've been using here from the beginning, and I'm going to go to what we did in the last section in 31 and find zeros. So I'm telling you, you have an imaginary zero of negative 2i. I want to find all the remaining zeros. So I'm going to start this one off similar to what I've been doing in the problems in here. So if I have negative 2i, that means I'm also going to have positive 2i. And if I start that off, then I would have x squared plus 4. Okay, again, squaring both sides, this would be negative 4. Add it to the other side, you'd have x squared plus 4. I'm going to take that and divide that into the polynomial. If you do it right, again, you should get 0 for a remainder. If you don't get 0 for a remainder, then either you divided wrong or what you divided by wasn't correct. Notice when I did this, I went from x squared straight down to number, so I was missing an x term. So I took that and inserted that in that spot with a 0. So you do the division, get 2x squared plus 5x minus 3. So I know I have 2i and negative 2i as two solutions. The other two solutions are going to come from the answer up here. So you're going to take that and either do factoring if it's factorable, which this one is, or quadratic formula to come up with the remaining answers. So I factored this, which would factor to 2x minus 1 times x plus 3. So now I would get 1/2 and negative 3 as the two answers from that. And then don't forget the initial two answers, 2i and negative 2i. All right, so you should be able to find a complex conjugate. With those complex conjugates, you should be able to write a polynomial that has real numbers involved in it, no imaginary numbers in there. And then take that idea and be able to find remaining zeros of a polynomial, given if I give you what the imaginary / complex zeros are. All right, so that's lesson 32 from chapter 4.